Welcome to the third in my series of videos about quantum mechanics without the maths. In the previous two talks we got quite a bit of mileage out of the example of a spinning coin, which could land either heads or tails. We saw that in quantum mechanics we didn't deal directly with probability distributions, but with wave functions, which are the square roots of probability distributions. We saw how we could combine wave functions to create other wave functions. We saw how the wave functions could have negative values as well as positive values. And we saw some rather bizarre effects, like the fact that a stationary coin could be represented as the sum of two spinning coins. We also had a brief introduction to the Heisenberg uncertainty principle. So the spinning coin has served us quite well, but now I'm going to move on to a different example. Instead of the spinning coin, I'm going to look at the roll of a die. So let's very quickly cover the basics of how we might model a quantum version of a die. It's got 6 possible values, so we need to have a probability distribution which has got 6 possible measurements. We can measure a 1, a 2, a 3, a 4, a 5 or a 6. In this case it's in the state with a 5 face up, so the probability of a 5 is 1 when it's in that state. Probability along that axis. Obviously if it comes up in any of the other states, a 3, it would be 3 along there instead, so it'd be in that state with probability of 3 and 0 probability for all the other faces. When the die is rolling and we've got no idea which value is actually going to come up, then we have to have equal probabilities for all of these. Now, of course, this is quantum mechanics, so we don't use probability distributions. We actually use the square roots of probability distributions. So each of these has height root 1/6, whatever that is. So if you want the probability of any particular value, say a 3 coming up when it's rolling, you look at the 3 component. It's root 1/6. Root 1/6 squared is 1/6. Which is the correct probability for throwing a 3. Now, of course, any or all of these values could be negative. We could have this. And if you squint your eyes, you can almost begin to believe that this is starting to look a bit like a wave. But you perhaps have to stretch your imagination a bit at this point. But the thing about our quantum die is, this is just as good a representation of the rolling die as this version is, where it's all positive values. And so in fact is the sum of these two wave functions. So you could add these wave functions where the odd numbers would reinforce each other and the even numbers would cancel each other, and you would actually end up with a wave function which only had odd numbers. This is an example of quantum interference. Now, obviously in a macroscopic object like a dice, we have no way of distinguishing between these two wave functions. We've no way of knowing how to create them or how to create a dice that is in one of these states rather than the other one. And so we've got no way of actually testing out this quantum interference on a macroscopic object. However, as we will see in later videos, that's not the case with a microscopic object like a photon or an electron. We will see how they have wave functions that really do look like waves. We'll see how there are equations which dictate how those wave functions evolve over time and how they can interfere with one another. Now, interference is a very important phenomena in quantum mechanics, but we can't really see it illustrated properly with the dice. So I'm going to move on to something that I think we can see with the example of the dice, and that's the idea of operators in quantum mechanics. The idea of an operator is that it can take one wave function and transform it into another wave function. So it might transform it from this state into this state, or from this state into this state. And there's a special class of operator that takes, it acts on one of the measurement states. So say the state for the dice being, showing the value 3. So there we go. When the dice is in that state with the 3 face up, and it's in this state here, probability of 3 is 1, and probability of all other states is 0. So we have a special operator called a measurement operator that takes this state and transforms it back into this state. So it gives essentially the same state out again, but this time multiplied by the measurement value itself. So it takes a wave function that has a peak value of 1 and multiplies it by the value 3. We're going to need a bit more room here, so let me rub some of this out. Okay, so our special measurement operator takes the state where the dice is showing the value 3, and it maps it to the same state again, but this time multiplied by the measurement value. Now, obviously, if it was the state 4, it would be 4 times that state. If it was the state 6, it would be 6 times that state, and so on. Now let's call this measurement operator D for dice measurement. So suppose we apply it again. We apply D, but this time to this wave function, the output of the previous application of D. Well, it does exactly the same again. It takes the state that was 3 times the 3 state, and this time it returns 3 times that, which is 9 times the 3 state. We call this combined operation D squared. But now suppose we created another operator. This time let's call it E. And E takes this basic measurement state where the dice is showing the value 3, and it goes straight as its output to 9 times the 3 state. So let's call that E. So in operator terms, applying the D operator twice, squared that is, to the 3 state gives us the same value as we get by applying E once to the 3 state. Now suppose we're playing a game with the dice, and the game designer has specified that when you roll the dice, you don't actually take the value that the dice shows as your score, but the square of the value. So suppose we call the value on the dice D, and the value that you score for the game E. Then the rule for the game is that D squared, the value on the dice, equals the score that you get, E. And this is exactly the same as you get by applying the operators, the D operator twice, or the E operator once. In other words, the equation that's followed by the measurements is exactly the same as the equation that's followed by the operators acting on the states. Now, why is this important? The reason it's important is that most of the time in quantum mechanics, unlike the cases we've seen here, when we did the coin, we knew what the 2 possible states were. We knew what the measurement values were. When we rolled the dice, we knew what the 6 possible values were. We knew how many values there were. But most of the time in quantum mechanics, we're dealing with situations where we don't know what the possible measurement values are. In fact, most of the time, what we're trying to do in quantum mechanics is actually to figure out what the possible measurement values are. What we do know are the operators. We'll see later on that we know the operators for energy, we know the operators for momentum, and it's the relationship between those operators in various physical situations that allows us to build equations. In particular, it allows us to build the Schrodinger equation. And we then take that equation, we apply it to particular situations with particular boundary conditions, and it gives us the energy levels and the states that are allowed in a system.